What's up, everyone? This is Premier Aerodynamics podcast number 16, and in this one, we're looking at the effects of speed brakes on the lift and drag of airplanes. And to do that, we're going to be looking at a paper called Aircraft Type Specific Impact of Speed Brakes on Lift and Drag. So, speed brakes, have pretty much all seen them. If you've been on an airplane, you've probably almost definitely seen them. Before you take off, you can see the pilot. If you look at the wings, the pilot lifts these little panels up and down, and then on landing, these little panels come up on the wings, and they're there to help the landing process, particularly the lift, which we'll go into today. So in this paper, they look at all these different aircraft, about 12 in total, and they look at the effects that these speed brakes have on lift and drag, because before this, it was just assumed that the effect was a certain amount, and it was very minor. So when you were designing an aircraft, you just say, okay, well, the speed brakes, they're going to be changing the lift by this much and the drag by that much. And even though they could be changing it by a lot more, you didn't really factor that in. So this paper goes into the different effects. So let's go through it. So they start off in the abstract saying to fully assess the performance envelope of these trajectories, so the trajectories of an airplane, the performance envelope means what conditions this airplane can travel at. Precise modeling of the influence of secondary control surfaces on flight performance is necessary. So the air brake, that is a secondary control surface. In particular, the use of speed brakes can significantly influence the descent and speed profile and allows the implementation of different cost indices. So what this means is the speed profile and the descent profile and the overall flight profile of an aircraft is how much time it takes for it to climb, how much time it takes to cruise, and then how much time it takes to descend, and then taxi and all of that. And that uses fuel and time. So knowing how the speed brakes affect this profile, you can then determine how long it will take for an aircraft to travel from one place to another. And that way you can factor in how much fuel it uses and how many times you can go back and forward and take as many passengers as possible. So going on, in this study, we present a modeling approach of the influence of extended speed brakes on flight performance and apply this method in a simulation environment for trajectory modeling of 12 different aircraft types. In doing so, we can determine an almost linear influence on the additional fuel requirement or the effective area of the speed brakes. So that's pretty cool. It means that if you know what the area of your speed brake is, you can determine what the amount of fuel that you need is. And then go on and say, the result can be implemented in any flight performance model and enable more precise modeling of future aircraft trajectories. Specifically, optimization targets regarding the required time of travel or the cost index of the consideration of the dynamic impact of atmospheric conditions in the trajectory optimization only becomes possible through the calculation of the influence of the speed brake on lift and drag. So this is a very important sentence here. It says a lot. What this is saying is you can calculate what the flight profile is based on all these different parameters. But if you don't factor in the speed brakes effects on lift and drag, then it's not going to be accurate, and it's really not worth much in terms of the actual operation. So that's how much of an effect speed brakes do have on lift and drag of an aircraft and other aerodynamic characteristics, as we'll go into. So moving on, they say to calculate the most efficient flight path in advance, powerful flight performance models are necessary, which calculate these trajectories depending on weather data, airspace information, cost requirements, and the performance data of the respective aircraft type. So you can't just take off whenever you want to. You need to determine what the weather is, if there are any other planes around, whether you have enough fuel to reach wherever you're going, and the aerodynamic performance of an aircraft. So for decelerating, speed brakes can be used with a significant impact on drag and a small impact on lift. This effect, in turn, may have a significant impact on fuel burn and is crucial for trajectory optimization. This impact will be shown in this paper. So then they go through what we know about speed brakes to date. They say, the impact of speed brakes on flight performance, i.e. on lift and drag, depends not only on the aircraft type-specific aerodynamic properties, but also on the speed and altitude of the aircraft. So there's quite a lot that it depends on. The impact of speed brakes is often not in the focus of relevant models, or is approximated by a constant factor of a change in drag of 0.02 and a change in lift of nothing. This is what I was saying earlier, where if you, before, and this was very common actually before computers came around and before we knew much about aircraft in general, when you were designing an aircraft and let's say you wanted to put a speed brake on there, you would say, okay, well, this will affect the drag by this much, in this case, 0.02, and it'll affect the lift by nothing. And this is just a standard that we use, but that's obviously not that accurate. And now that we do have computers and more information, we can get a much more accurate understanding of what the speed brakes do to lift and drag, and that way we can understand we don't need to have as big a safety factor when we're calculating flight envelopes and flight profiles. So moving on, older experimental studies focus on the effect of speed brake deflection on lift coefficient and pitching moment. So the pitching moment is just, for those of you who don't know, it's whether the nose goes up or down, or the tail goes down or up. Same thing. Because of the high relevance for controlling the aircraft. So the pitching moment is very important for determining the lift. So if you want to increase the lift, you often nose up the aircraft. That then increases the angle of attack for the wings, and then you produce more lift. Although from the aerodynamic and flight performance point of view, the effect on the drag coefficient is more important. It has often not been measured and evaluated. Furthermore, experimental data only account for the pressure element of the drag when using absolute drag coefficients, ignoring the viscous contribution. So pressure drag accounts for quite a chunk of an airplane's drag, but viscous drag is actually quite important as well, particularly at low angles of attack. So around the 0-1 degree angle of attack, viscous drag can be 20-30%. And when you go to high angles of attack, then that's when pressure drag becomes far more dominant. So moving on, McLaughlin experimentally analyzed steady and unsteady flow fields generated by a typical two-dimensional transport air force spoiler configuration without specification of the wing, and reported a decrease in lift coefficient up to -1.2 for a speed brake deflection angle of 60 degrees. And that's huge. So this was at an angle of attack of 0 degrees. If the speed brake deflection is 60 degrees, so the wing is at 0, but the speed brake has been popped up, you get a lift reduction of 1.2, way more than 0, which was the standard that most people used. And what's more, if you increase angle of attack up to 16 degrees, so the wing now is at 16 degrees, the impact of speed brakes on the lift coefficient decreases to -0.8. So that means that increasing the angle of attack reduces the effect of the speed brakes on the lift coefficient. Now, Abdelrahman and others experimentally studied the effects of spoiler configurations on the aircraft aerodynamics of a B747 airplane under wind shear conditions, and showed that spoiler deflection enhances the wind shear induced lift loss, especially at low angles of attack. They published experimentally gained values. So for an angle of attack of 16 degrees and a deflection of 90 degrees on the speed brake, the lift coefficient increases by 1.25, corresponding to minus 70% of the lift at 16 degrees and a deflection of 0. And then if you have a angle of attack of 4 degrees and the deflection angle of 90 degrees, the change in the lift coefficient is 0.6. So it does change a lot. Wind shear tends to amplify the spoiler effect on the side force and yawing moment, but only at a high angle of attack does it alter the resulting rolling moment. So that's interesting. It shows the variability of these speed brakes depending on the orientation of the aircraft to begin with. Furthermore, Abdelrahman and his colleagues proved that speed brake deflections, on the other hand, have almost no influence on the aircraft stability margin, which is generally increased when wind shear is present. So the stability margin is exactly what it sounds like. It's the margin that an aircraft is stable in. The greater this margin, the more stable the aircraft is seen to be, which means that you can push it to a weirder orientation and you'll still be able to stay within the stable position. And this also means that typically you reduce the maneuverability of the aircraft, but for passenger aircraft, this is great because you don't want it to be too maneuverable, you want it to be very stable. So moving on, Lindsay and colleagues experimentally proved that at high angles of attack, so angles of attack above 16 degrees, and high deflection angles above 25 degrees, the spoiler airfoil on top of a NACA 2412 airfoil created even less drag and more lift than in a clean configuration. So what that means is that using a spoiler on this particular airfoil, a NACA 2412, is actually better, a better performance. You get a less drag and more lift. Beyond these extreme conditions, they gain similar results for the increase in lift. So the lift reduced by 0.375 and the drag increased by 0.05. The dynamic impact of speed brake deflection on lift and drag and gain results in the range of a 0-degree angle attack and deflection of 60 degrees of what we just mentioned is fairly large, and again shows that speed brakes do affect the lift and drag of an aircraft a lot. So moving on, all experiments show a greater influence of speed brakes on the lift coefficient and drag coefficient than assumed. So there's 0 and 0.02 respectively, which is why they're doing this research. From the literature studied so far, it follows that either unsuitable aircraft types were considered or important dependencies such as speed and altitude are missing in experimental setups and published values of the change in lift and change in drag coefficients. The results do not make it possible to evaluate a general model for the impact of speed brake deflection on lift and drag. And more research is needed, obviously. So they then go into their research and they say by using the speed brakes, steeper flight profiles can be flown without exceeding the speed limits of the aircraft type or the airspace currently being flown in. So let's talk about this. So what does this mean? When you use speed brakes, why would you be able to have steeper flight profiles? So in a typical flight profile of an aircraft, you have, let's just break it down to very basic components. You have the takeoff and the climb, then you have the cruise, then you have the descent and landing. So the descent and landing takes a certain amount of distance to do. So when you're, let's say, 200 kilometers out from a city or however far, you then start descending. And this is because of how quickly you can descend. So if you can use a speed brake, you can actually wait until longer. So let's say you're only 150 kilometers out from the city instead of 200 before you start descending. That means that you can travel faster. You can go through cruise for a longer distance, which means that you get to the city quicker. So that's why you can have a steeper flight profile, because you can descend quicker. And that also means that you don't have to travel as fast to get to your destination. You can travel slower, or you can travel the same speed, get there quicker, and then you can ferry people back and forth between two destinations even quicker. So the angle of the speed brakes can be set on all commercial aircraft using a lever in the cockpit. The principle for speed brake setting differs not only according to the aircraft type and position of the wing, but also depends on the manufacturer as concerns the type of activation. For example, the manufacturers of Airbus and Bombardier have fixed dents for the various angles of the selection lever of the speed brakes, while Boeing and Embraer allow the pilot to adjust them continuously. Most of the secondary control surfaces acting as rolling spoilers are used to support the ailerons to increase rolling moment along the longitudinal axis to initiate turn maneuver. So let's talk about this. So on an aircraft, you have a whole bunch of control surfaces. You have wing flaps, you have ailerons, you have then these different types of air brakes, these speed brakes. And so ailerons are typically used, they're usually further outboard on the wing, they're near the wing tips. And the reason why you put them so far out is because the further out you put them, it means the greater the moment arm is. So you're rolling about the longitudinal axis, so the middle of the aircraft. So if you go further out, that distance increases, which means you don't need as great a force to be able to roll the aircraft, which means you can get away with smaller control surfaces. Now, using air brakes or these speed brakes, you can also use them to help roll. If you pop them up, that changes the lift on the wing, and then you can use them to also roll. So they help support this aileron function. So since the spoiler panels serve to reduce lift, they are extended on one side of the wing for a turn maneuver. So if you reduce the lift, that means that the other side of the aircraft is producing more lift, and that's going to result in this roll, this imbalance in force, which is going to result in a roll. Resulting asymmetric lift causes the wing to sink on one side, which creates a moment about the longitudinal axis. As roll spoilers have two functionalities, one as spoilers and the other as ailerons, they are also called spoilerons. Unlike ailerons, however, spoilers can only be extended upwards and thus only reduce lift and do not increase it, whereas ailerons, they can go up and down. So they typically work in unison. If one side, the aileron goes up, the other side, the aileron goes down. So you have this two-way change in lift. Since modern flight control systems always combine yaw and roll moments to initiate a turn, the spoilers also take over part of the function of the rudder, so that it does not have to be additionally deflected to initiate the turn. So this is an interesting point here. One thing that I want to talk about is, so since modern flight control systems always combine yaw and roll moments, this is actually something that's called inertial coupling. So when you have an aircraft, often when you change the direction of the aircraft in one direction, it will change in another direction as well. And if you have high inertial coupling, it means that there will be a very large change in the other direction. And this is quite good for maneuverability. It also can mean that you can get away with smaller control surfaces or less of them, but it also means that it's way more complex and you often need computers to help fly. In fact, there are some, if you take it to the extreme, there are some fighter jets since about the 80s that they made these aircraft inherently unstable with very high inertial coupling. That means that they can maneuver very quickly, but because they are so unstable and they're also hard to control, you actually need a computer to control them, and a human can't control them. They don't have the reaction time needed to control these type of aircrafts. So this takes it to the extreme. On commercial aircraft, that's often not the case. You want them to be far more stable. So ground spoilers, so these are different types of spoilers now. They're on the wing still, but they have different functions. These ground spoilers are extended to their maximum angle during landing to reduce lift as much as possible. The additional drag caused by the ground spoilers, on the other hand, plays only a small role during landing. So this is very interesting because you typically assume when you see this massive air brake come up that this is reducing the drag, and that's this primary function, but the primary function is actually to reduce lift as much as possible. And the reason why is so they go on and say the lift on the wing in the area of the spoilers is eliminated since the airflow can no longer be applied. During so-called firm landing procedures, the landing gear is pressed more strongly onto the ground for increasing the efficiency of the brakes. So this means is by dropping the lift so much, you can then rely on the brakes to arrest the aircraft instead of using aerodynamic drag to arrest it. So this is one way of bringing the aircraft to a stop. After touchdown, it is important to reduce as much lift as possible as quickly as possible so that all existing spoiler panels are usually extended to the maximum angle as ground spoilers. So why is it important to come to a halt as quick as possible? One of the main reasons is that you only have so long a runway. The bigger the aircraft, typically the longer the runway you need, both for takeoff and landing. What's more, if you have a runway, you often have other aircraft on there as well. So you don't want to take up all this space, you don't have to, because that means that other aircraft cannot use it. The less space you use to land and take off, the more airplanes you can have landing and taking off, which means that the space is used far more efficiently, which reduces costs. And it also means you can fly more aircraft and get people to where they want to much quicker. So modern transport aircraft use flap spoilers. A flap spoiler is a panel fixed to the wing upper surface trailing edge region that, when deflected upwards, the panel rotating about its leading edge causes the flow to separate over the wing surface in a controlled manner, resulting in a decrease in lift and an increase in drag. So this is very important to be able to do it in a controlled manner. Due to the current inability to simulate separated flows, speed brake aerodynamic properties are the most challenging of the airplane control surfaces to anticipate. Speed brakes have a number of characteristics that make them ideal for lateral control in aircraft. Large rolling moments are produced by speed brakes, and speed brakes are an alternative to ailerons for full roll control, allowing full span flaps to be used, with apparent STOL uses and benefits. So STOL is short takeoff and landing. So as you mentioned earlier, having these air brakes or speed brakes or spoilers, whatever you want to call them, they can help with this roll, which means that you can have them take over much of the work that the ailerons do. So you're having these multi-purposes because they then also serve this stall uses and benefits. Ailerons provide an undesirable yawing moment, whereas speed brakes produce a favorable yawing moment. So again, this is an inertial coupling that I was talking about earlier. When you change the role, the yaw also gets affected. In the case of ailerons, this is undesirable, the way that they do it. With speed brakes, it's favorable. Furthermore, speed brakes, as opposed to ailerons, are usually more effective at high speeds and are less prone to suffer from aeroelastic effects. So aeroelastic effects include something called flutter. You've probably seen videos on YouTube and elsewhere where like you have an aircraft, often it's a fighter jet, and you see the wings just start flapping, like there's like this wavy motion to them, and this actually is very unstable and it can actually disintegrate the wings, and it has happened. It's a kind of a nightmare for most pilots and aircraft designers because aeroelastic effects are usually the hardest aspects of the aerodynamics to get right. If you get them wrong, then you can have this flutter, and this produces problems during the testing phase and can cause casualties, which is why it's so important to get it right. So speed brakes are very beneficial for damping these effects out, whereas ailerons are not as good. Unfortunately, several of the aerodynamic characteristics of spoilers increase the complexity of predicting this unsteady flow field generated by airfoils with deflected speed brakes. The speed brake control effectiveness is nonlinear. The lift decrease is a nonlinear function of the speed brake deflection. This nonlinearity is most noticeable when speed brakes are employed in conjunction with a deflected flap. This requires the speed brakes to be integrated with other control surfaces such as ailerons in order to give linear control, which is necessary to satisfy the pilot and autopilot functions. When the speed brake is deflected, the resulting turbulent wake is extremely unsteady. The wing interacts with the horizontal tailor and buffers. So again, this is potentially some sort of flutter. Furthermore, the time delay between the deflection of the spoiler and the reduction in lift causes a delay in the aircraft's response to speed brake deflection. Finally, the change in wing pitching moment with spoiler deflection, as well as the influence of the spoiler wake on the horizontal tail, can generate unacceptable pitching moments. So those are just some negative effects of speed brakes. So now they go into testing these speed brakes on different aircraft. So for example, in this one, they're looking at speed brakes on NASA model B747. The B747 consists of 6 speed brakes per wing. That's a lot. 6 speed brakes per wing are extended synchronously, whereby the inner speed brakes can only be extended by 20 degrees compared to the outer speed brakes with a maximum angle of 45 degrees. So this means that the outer speed brakes can be deflected far more. In addition to the theoretical calculation explained, Hanke, another author, calculates the modified coefficients for each speed brake panel, separately using Boeing-specific performance coefficients. These speed brakes depend on speed brake angle, altitude, angle of attack, and flap configuration and speed. And now they just go through these equations that they're deriving to use speed brakes. I'm not going to go through them because they're quite boring just to read aloud. If you're interested in them, you can look at this paper. It's open access again, so you can access it very easily and go through them if you're interested. Let's move on to some of the results. So they say, it can be concluded that when comparing different speed brake panels, the wing depth at this point has little effect on the speed brake impact, and the variation of the speed brake angle is more relevant. So one thing I want to talk about is the wing depth. I am not too familiar with this term. I looked it up, and there's no clear definition of this term, but from what I can ascertain, it's how far down, from the leading edge the speed brakes are installed. And what they're saying is that this distance doesn't really affect the speed brakes performance very much. The far more relevant parameter is the angle that is deployed at. So that's interesting. It shows that the aircraft is fairly insensitive to how far down these spoilers are placed. Note that this fact is only valid for laminar flows adjacent to the profile in a subsonic range, a consistent angle of attack, and a clean flap configuration. So these 3 parameters or considerations are quite important. So subsonic range, that's fine. Most aircraft travel in subsonic range anyway. Constant angle of attack, that's pretty good. Sometimes there is a change of angle of attack, so that's sometimes not the case. And a clean flap configuration. So this is again kind of in the cruise condition. Furthermore, maximum speed must be well below the speed of sound, so below Mach 0.94. That's not too bad. That's most aircraft travel below that. Now, they not only looked at that B747, they looked at 11 other aircraft. So they looked at Airbus ones, A310, A319, A320, A321, A330, A380, so the big one. Then they had Boeing models 737, 767, 777, then the Bombardier CRJ 900, and the Embraer E170 and the E190. So a whole bunch of different ones, from very small passenger aircraft and very large passenger aircraft. And they looked at how their models affected these flight profiles. So they say figure 4, so just figure 4 in the paper, depicts the change in the lift coefficient and the drag coefficient for an Airbus A310. Depending on the speed brake angle at 30,000 foot altitude and Mach number of 0.82, with the flaps in clean configuration and an angle of attack at 0 degrees. As expected, the total lift coefficient decreases and the lift drag coefficient slightly increases with increasing speed brake angle. So that's pretty good. That's what they're supposed to do to some extent. For the 12 aircraft types mentioned, it was possible to determine the change in the drag coefficient and lift coefficient, which can be classified in a respective performance field of the aircraft types and thus allow good comparison possibilities of the individual types. So this is a big step forward, because before this, remember how I was saying that when you were designing an aircraft, you just say, okay, the speed brakes change the lift and drag by this much across the board. It doesn't matter what aircraft you're looking at, that's what it's doing. Now they're looking at each individual aircraft and they're finding that they do change slightly between different aircraft, and now we've got a pretty good model for that. So we don't just have to assume that the speed brakes are doing the exact same thing for each aircraft. We know that they're not, and we know how they are changing. So now they look at the benefits on this and the detriments for the flight profile on a B777. So they say, from its large speed brake area, it thus achieves a maximum reduction in descent time of 265 seconds. So that's 4 minutes. That's pretty good. Now, interestingly, this results in a reduction of the descent distance by 51 kilometers between retracted flaps and maximum flap position. So that's pretty massive. Like, that means that you can travel an extra 51 kilometers in the cruise configuration before you have to descend. So that means you can go faster and you can get to your destination quicker. To determine the possible impact of speed brakes on fuel consumption, now this is an interesting thing. We've been talking about how the lift and drag coefficients get affected and the flight profiles. We often assume that if there's a general positive effect for the lift and drag, that the fuel consumption is going to be positively affected as well. But they're going to go into this now. So they say to determine the effects of speed brakes on the fuel consumption, flights from Dresden, so Dresden, Germany, don't mention the war, they're still upset about it, starting at a cruise altitude of 25,000 feet are examined. By shortening the descent section, the aircraft remains at cruise for longer and thus flies with the thrust setting for cruising flight for longer, which is above the idle setting during descent. So this means that they're in a powered flight, a significantly more powered flight for longer of this trip than if you didn't have these speed brakes deflected, because during descent, you just put your engines on idle instead of really giving it the beans. As a result, the total amount of fuel required for the flight increases. It follows that the use of the speed brakes leads to a lengthening of the cruise segment, and this, in turn, leads to a larger amount of fuel required for the entire flight. At the same time, however, a shortening of the descent time becomes possible. The time savings are very small compared to the total flight duration. The reason for this are the steep angles that can be flown by using the speed brakes, especially in the long-haul models. The problem with long-haul models is that the descent, it takes up a very short amount of time compared to the entire cruise. So the further you're traveling, the less important these speed brakes are going to be in terms of saving time, because if you're traveling 10 hours by plane, being able to save 3 minutes at the end is not a huge deal. But you are going to be increasing the amount of fuel that you use, so that's not a great idea. If you're on short-haul flights, for example, Washington, D.C. to New York, that's much shorter, so you can then take advantage of these shorter descent times and cram in more flights and get more passengers going and make more money that way. So perhaps the increased fuel consumption is worth it. Due to the steep angles, the descent phases have a low horizontal speed component, which is why less distance is covered in these phases. While this also leads to a lengthening of the cruise flight with a greater horizontal speed component, it reduces the savings potential of the total flight duration. So that's how speed brakes affect an airplane's performance. They change the lift and drag, usually positively in terms of the descent time, but negatively in terms of the fuel consumption. So make sure to check out all the instrumentation that we make here at Premier Aerodynamics to make your experiments better. Check out the courses we put on for all theoretical, experimental, and numerical to make you a better aerodynamicist. And check out our conference, International Aerodynamics Conference, we put on every year so that all aerodynamicists get together and talk about what we love doing. So make sure to like and subscribe, and I'll see you in the next podcast. Peace out.